This is the final installment on the VCO design. Up till now we've used CAD tools to lay out our circuit. We took our VCO and we divided it into a resonator network and into an active network. We incorporated adjustable components in our network, but so far the whole process has been a methodical development of as simple a circuit as we could, noting that we have parasitics that occur at microwave frequencies that we wouldn't have to worry about at low frequencies. Here is our VCO schematic. So the full schematic is shown on the top. There's a dividing line between the resonator network and the active network, and those networks are broken out at the bottom, in particular showing how we measure gamma D and how we measure gamma R, the reflection coefficients looking into the active device and into the resonator network. And we've inserted a number of components that we can adjust. We have adjustable features, 2 adjustable features in the resonator network. The capacitors at the top enable us to fine-tune the capacitance range. This is a VCO that we want to be able to tune from 4.5 GHz to 5.5 GHz. And we achieve that tuning by changing the capacitance of those stacked varactor diodes in the resonator network. And we have those additional 0.5 picofarad capacitors, 2 capacitors in series, of course giving us a 0.25 picofarad capacitor, but we could have needed some other values. So those values of capacitance are used to fine-tune the capacitance values that we can get from the varactor diodes, because in fact there isn't a large variety of capacitance values that we can get. So we can fine-tune the tuning range. Another one of our adjustable elements is this variable short circuit that we're going to have at the end of our transmission line resonator. This tapped connection is also variable, but once we've laid out the circuit, it's pretty much fixed. On the active network, we have 2 variable capacitors, CA and CB, and we use CA and CB to adjust the locus of gamma D. So we're going to use it to shape the reflection coefficient curve. We introduce CA and CB in part to accommodate the frequency-dependent parasitics of our active device. That inductor at the base is the inductor in the Colpitt's oscillator design. It's shared between the output network and the input network. But that inductor has an impedance that varies with frequency, so the amount of feedback varies with frequency. Now, if we were designing a VCO that was over a fairly narrow tuning range, we would not have to worry about that. But going from 4.5 GHz to 5.5 GHz, that impedance changes significantly, so the feedback element in the Colpitt's network changes quite considerably, and we need those capacitors to accommodate for that as well as all of the other parasitics. Here is the layout of our final VCO circuit. We've clearly divided the circuit into a resonator network and an active network, and you may notice that these networks are very close to the schematic diagram, and we tend to do that as well so we can understand our circuit a lot easier. So the resonator network is on the left, the active network is on the right, and here are our adjustable features, the same features that we had before. And now we can see how we vary the length of the transmission line. We have a 0 ohm resistor here, a shorting bar if you like, that we can move up and down in this direction to fine-tune the resonant frequency of our resonator network. Our transmission line goes from this top connection, and we have a tapped connection here. This is our tapped connection. Our resonator network is on this side. The active network connection is right here. The transmission line is shorted at the bottom. So we have 3 vias here, so we're providing a low resistance short. And we have a shorting bar connected to a strip that is connected to the vias in multiple places. So we will move that shorting bar up and down, or a person at the final product tuning stage, because each item will have to be tuned, will sit there and move that tuning bar up and down. We're not establishing a short circuit right at this point. It's kind of a little bit fuzzy really exactly where that is, but we are varying that short. On the active network side, we have a capacitor CA here and CB. They're the same capacitors we had before, the capacitors that we use for reflection coefficient shaping. And here's a little bit more detail on our resonator and active networks. The connection is from that point there where we measure gamma R and this point here where we measure gamma D. So gamma R and gamma D are reflection coefficients that we determine in simulation, but we also measure these because we find in microwave circuits, especially above a few gigahertz, that simulation on its own is not enough to get a working circuit, because in simulation we can't take all possible effects into account. Yes, we can use EM simulation as was done here with all the results that have been presented up to now. We use 2.5D simulation, but these components are not flat. They are little cubes and there's sidewall capacitance, and there are many things that we can't take into account. We also assume that our solder paste, for example, has 0 ohm resistance, and it won't exactly have 0 ohm resistance. So the art of microwave design is that we will use simulation, we will use intuition, and we will use measurements, and we'll use all of those to guide us towards a final product. Now let's talk about how we're going to do the measurements of our network. Well, we're going to take the circuit board and we're going to cut it in half to separate the active network from the resonator network. And our measurements are going to be done in a 50 ohm system. So we need to use a 50 ohm test fixture, first at the interface with the resonator network and then at the interface with the active network. And what is shown here is an SMA connector. So these are very small connectors. This is about 4 millimeters across here. So this is certainly blown up. And on the right hand side here we have our connection. There's a pin coming out from the connector. And this large block here is our flange. There are going to be field lines that terminate on the flange. So we are changing our active network a little bit. And the SMA connector looks largely like a transmission line, but there are parasitic elements and there is loss as well. So we have determined that the length of this SMA connector corresponds to a transmission line that delays the signal by 35 picosecond. So the round trip delay is, well, starting at this point, 35 picoseconds to the active network and then back 35 picoseconds. So the 35 picosecond delay is due to the length of the SMA connector, and it is required, of course, to reference the measurements of the active network card to the vector network analyzer we're going to use. There are cables from our vector network analyzer. We will calibrate fairly precisely to the ends of those cables, and then those cables are going to be connected to the SMA connector. The period of a 5 gigahertz signal, which is in the middle of our VCO band, is 200 picoseconds. So we have a 35 picosecond delay telling us that the connector has an electrical length of 63 degrees. Now we're going to do reflection coefficient measurements, gamma R and gamma D. And so the reflection coefficient is going to be rotated by twice that. The reflection coefficients are going to be rotated by 126 degrees. So our measurements must be corrected. This 35 picosecond delay does not describe the impact of the SMA connector completely. There will be parasitic capacitance and inductance. There will be some parasitic resistance. So the correction will not be perfect. If we wanted to be a little bit better, we could use a different electrical length at one end of our tuning range and at the other end of the tuning range. But there are enough imperfections here that it is worthwhile sticking with something that we understand intuitively, and we understand this 126 degree rotation. So here are raw measurements These are the raw measurements that we obtained in the lab. So we're doing a measurement here of the resonator network, and these need to be corrected. So our actual measurements need to be rotated by minus 126 degrees because the transmission line length of the SMA connector took our actual gamma D and rotated it by 126 degrees. So we need to take our raw measurements and rotate them counterclockwise. And so here are our corrected measurements. Of course, this correction will not be perfect, but it is a lot better than not doing the correction at all. In fact, not doing the correction would completely throw our intuition off. So this reflection coefficient is measured with a tuning voltage of 3 volts. Here are the measurements of gamma R again with a tuning voltage of 3 volts, and also shown here are the characteristics of our active network with a small signal. So we're taking our active network, we're connecting a 50 ohm cable to our SMA connector, so we're loading the active device by 50 ohms, and this device does not oscillate if it's loaded by 50 ohms at that resonator connection. We're doing measurements at fairly small signals, could be in the tens of microwatts range, so it's a fairly small signal. We're not driving the transistor so strongly that we're seeing nonlinear effects. These measurements were made with Ca equal to 0.5 picofarads and Cb equal to 0. Now, as the signal level increases, if we look at our measurements, and as the signal level increases, this 1 over gamma D curve moves to the right. And that is what we're trying to achieve in our simulation as well. It is the intersection of the 1 over gamma D locus, as amplitude increases, and gamma R that determines the oscillation frequency and the signal level. Now, at small signals, the intersection is right here. This is actually not desirable. We would like that dashed 1 over gamma D curve to be parallel to our gamma R locus. But at least we have a single point of intersection here. But as the signal level increases, this locus is going to start looking like this. And with a little bit of wobble due to parasitic effects, we will see that there are multiple crossings here. And in fact, when we set this VCO up with these capacitance values, multiple oscillations were seen. And so these are clearly undesirable. Now, we've worked out a strategy already to remove these multiple oscillations and obtain single frequency stable oscillation. The concept was to change the shape of the 1 over gamma D curve. Before we go any further, let's compare the simulated responses and the measured responses. The simulated responses are shown on the left, the measured responses are shown on the right. Clearly, there is a correspondence, but there is a difference, of course. So the question that comes to mind is, which set of results should you believe? Should you believe the simulation, or should you believe the measurement? Well, the truth of the matter is that neither of them are likely to be perfect. The simulated response looks very smooth, doesn't it? It does not show the effect of the many parasitics that we have not been able to incorporate in simulation, such as the sidewall capacitances of components. On the measurement side, we are doing measurements of resonance circuits, and they're always very difficult things to do. For example, this crossover point that we simulated corresponds to a conductance of 0.4 Siemens or 2.5 ohms. When we make a connection, during measurements, for example, it is very difficult to have less than a half ohm resistance. Any resistance that we introduce when we're trying to do a measurement of our resonator is going to have a significant effect of the resonator. So my interpretation of what we're seeing is that the resonance is more likely to have the shape that we see on the left-hand side, the simulated shape. And what we're seeing on the right-hand side, to me, looks as though we have just a little bit more loss. We're kind of killing the Q of our resonator network. But the basic characteristic is there. Another thing you will notice is that it looks as though the whole curve, the gamma R curve, has been rotated a little bit as we increase with frequency. Well, the result of this is that we did a correction that was valid, reasonably valid anyway, at 5 gigahertz by rotating the raw measurements back by 126 degrees. Well, in fact, at 3 gigahertz, the electrical length is shorter, so we shouldn't have rotated as much. And at 6 gigahertz, the electrical length is longer in terms of degrees, and we should have rotated it back further. And so everything would have come together. But we don't have to be very precise here. We're trying to establish an understanding of what is happening in our circuit. Both of these results are for the situation where we have CA equals 0.5 picofarads and CB is equal to 0, and the tuning voltage is 3 volts. In simulation, we see a situation where we have multiple crossings. Now, our oscillator simulation will not tell us if we have multiple oscillation. It is set up in a harmonic balance simulator, and it'll only give us the answer that we're telling it to give us. And that answer is, what is the frequency of oscillation? If there was no frequency of oscillation, it would tell us that. In fact, the simulation would never converge, and eventually it'd say a simulation couldn't be found. And when we did the measurements in this situation, we did see multiple oscillation. And now, from simulation, we interpret that by these very clear multiple crossovers. And when we go over to measurements, we want to see if we can see the same multiple crossovers. Well, we don't see it at small signal, but we will see it as the signal slowly grows. Now, I did say that we have introduced some parasitics in our measurements, and we've dampened down the resonance, and that's the reason why those red gamma R curves look a little bit different. But we've also introduced parasitics into our active network, and so the measurement we have here of 1 over gamma D, the small signal measurement of 1 over gamma D, is not likely to be correct as well. But just think of our whole design process. We started off with a basic Colpitt's oscillator in a common base configuration. We added just a few components to get the performance that we really wanted, such as the stacked varactor diodes, and then we introduced tuning elements. And we can use those tuning elements to correct things. For example, I believe that this resonator shape is fairly accurate, but the exact frequency could be off a little bit because of our parasitic capacitors. I can change those capacitors, the 0.5 picofarad capacitors that were between the stacked varactors and the transmission line, to fine-tune the frequency at which this resonance is occurring. So let's summarize the difference between the simulation fidelity and the measurement fidelity. Now, our simulations used EM simulation of the passive components and the layout. It used 2.5D EM simulation. 3D simulation of a structure like this would be very difficult. Now, 2.5D simulation assumes that we only have current flow in the XY direction, a flat plane, or in the vertical direction. We cannot take into account the effect of the finite thickness of these various lumped elements. Now, these lumped elements are almost as thick or high, if you like, as they are wide. And so there's quite a lot of sidewall capacitance, and they cannot be taken into account. There are also model limitations. We cannot get a tremendous model for the varactor diodes, or even for a fixed diode or a lumped inductor. So, because of parasitic coupling, which could be electric field-based coupling or magnetic field-based coupling, these elements affect each other. Just placing them near each other will affect components on the other side. We have limitations with our measurements as well. For one, the connection resistances are not accounted for, and something as little as a 0.5 ohm resistance would have a tremendous effect, especially when we're near the resonator. The full effect of the SMA connector was not accounted for. There will be small parasitic inductances and capacitance, as well as that overriding transmission line characteristic. and we haven't taken all of these into account. So there are parasitics of the connectors, and just the act of measurement has changed the field lines. For example, there will be field lines that terminate on the flange. They were certainly not accounted for in simulation, and there's really no way to correct our measurements to remove that effect. This is the measured large signal characteristic. So how did we arrive at this? Well, we have done a measurement of just the active network on its own. We've removed the resonator. We've connected our network analyzer at the SMA connector connected to our active network. The 50 ohms that the active network sees suppresses oscillation in this case, and we're going to drive that SMA connector port with a signal, in this case a signal with a power of 10 dBm. So we're driving this circuit with a single sine wave. When our oscillator is oscillating, there will be some harmonic content there as well, and we clearly can't drive this circuit with harmonic content. So we're not creating a large signal situation that corresponds precisely to the large signal oscillation configuration, but we are seeing what we expect. So we're driving the circuit at 10 dBm, and we see this 1 over gamma D curve moves to the right, and it hugs, in this case, the unit circle. Now we have some parasitic resistances, so perhaps our signal is looking like this. But this is the type of characteristic we want. We want this 1 over gamma D curve to follow a line of constant conductance, or approximately a line of constant conductance, when the signal level has built up. So we see some other effects here. We see some wobbling around. In fact, we see a little loop here which indicates some resonance. Perhaps that resonance was introduced by the very measurement fixturing that we had to employ. I kind of doubt that that resonance is going to be in our active network anyway. And besides, this oscillator works, and it has really good characteristics, and it can be tuned over the full tuning range, which makes me even feel more confident that that loop is spurious. What our large signal measurements have told us is that our characteristic for the active device, that is the 1 over gamma D characteristic for the active device, does move right as we wanted to, and it does tend to saturate on a constant conductance line. Remember, we have a number of adjustments that can be made. These are the adjustments we can make to the resonator network. We have these capacitors at the top here, and when we lay out the circuit, here are the capacitors, and then we can vary this effective short circuit, which is done by varying that shorting bar. Our layout is very close to the schematic, and that is a common characteristic with microwave circuits. In fact, with all circuits, we like to lay out the schematic so that it is fairly close to the layout. But with microwave circuits, where we have transmission lines and we are concerned about components coupling to each other, we try and follow the layout closely. So let's look at the active network now. The two main components we can adjust are CA and CB. Here is CA here. Red on red doesn't look so good. And here is CB. And this in here is our BJT. And this is the connection to the resonator network. So when we are designing our circuit, we design a circuit that is fairly easy to understand, fairly easy to do measurements. Now let's look at some measured characteristics, the final characteristics of our VCO. Here is our measured tuning curve, as it is called. Our tuning voltage is at the bottom here. This is the voltage that's applied across our varactor diode. We can vary that from 0 volts up to 9 volts. Our oscillation frequency varies from just a little bit over 4.5 gigahertz up to 5.3 gigahertz. And an important parameter is the sensitivity, sometimes called the tuning gain. And this is expressed in terms of megahertz per volts in this case. Perhaps in some cases it'll be expressed in terms of gigahertz per volts, but megahertz per volts gives us a fairly good round number for microwave VCO design. So that's a nice characteristic. I guess what we would ideally like would be a straight line between the frequency and tuning voltage, but we're not going to achieve that. The CV characteristic of a varactor diode, of course, is not linear, and so we must expect this variation. This is the measured output power and the power of the harmonics, and this is measured at that V out point. This is the point before we hit the attenuator and followed by the bandpass filter. So it really is the output of our oscillator. The attenuator and the bandpass filter are introduced to isolate our VCO from the external circuit. Some of the characteristics we would really like is a fairly flat power of the fundamental as we vary the tuning voltage, and that's exactly what we see. That is a great characteristic. We see fairly low second and third harmonic levels. The second harmonic level is higher at the low tuning voltages because that's of course where our varactor diodes have the most nonlinear CV characteristic, and that third harmonic is really low. So that's really good. We like to have a nice sinusoidal oscillator. We do not want power generated that is dumped in the harmonics. That also means that noise at the harmonics, such as white noise at the harmonics, is not going to affect the operation of our oscillator. So that's going to reduce our phase noise. One of the most incredibly important characteristics of an oscillator is the phase noise. So here is the measured phase noise. This is the phase noise that's measured at the two extremes of the tuning range, 4.5 gigahertz and 5.3 gigahertz, and also in the middle at 5.1 gigahertz. Now, lower phase noise is better, and if we're designing a VCO, it is the worst case that matters. Many academic papers just pick the best result, but in fact, that's not the important thing if we're building a product. If we're building a product, it's the worst performance that counts. Our worst performance is this top curve here. That's the curve at 4.5 gigahertz, and it is fairly standard to compare oscillators by looking at the phase noise at 1 megahertz offset from the carrier. So here our phase noise, 1 megahertz offset from the carrier, is minus 130 dBc per hertz, which is a very good result at 5 gigahertz, or in this case 4.5 gigahertz. We do better even as we go to higher frequencies. So here is a VCO that has a very wide tuning range and very low phase noise, state-of-the-art phase noise. In summary, microwave VCO design should be approached as a methodical process. In fact, all microwave design should be approached as a methodical process. This applies to all forms of microwave design, RFIC design, hybrid design. Anything above, a few hundred megahertz really should be approached this way. We must use intuition. We must have a very precise plan that we're going to follow. And we see that our circuits are really based on some very simple topology, like a Colpitts oscillator. The Colpitts network has been known for a very long time, and we still use it. We add components to the Colpitts network to correct for things or to achieve something like tunable frequency of oscillation, but still the fundamental core of our design has been known for a very long time. We need to use simulation together with measurements to guide this methodical design process, and of course intuition is very important as well, because we cannot expect our simulation and measurements to agree. If they did, that would be too easy. So as technology progresses and as our simulation capabilities improve, we can expect our simulation and measurements to be more closely correlated. It is critical that we build in adjustability in design. When we're doing hybrid design, such as we're doing here, we can build in our adjustability by being able to change lumped elements, or a good example is this shorting bar that we can move up and down to vary the length of the transmission line. If we're on chip, we're going to use biases to adjust things such as capacitance values, but we must build in adjustability. In fact, one of our challenges is how to do this adjustability automatically without a human being in the loop. And if we can do it automatically, we will be able to adjust for operation at different temperatures and as our circuit ages. And the other thing to remember is that microwave circuits nearly always requires tuning of each item that we produce. Whether we are building an RFIC or a hybrid circuit, there will be manual tuning involved, most likely, and so part of our design effort is to minimize the cost of manual tuning. We can do that by having fewer stages. For example, having a VCO that operates at a fairly high frequency is much better than having a low frequency VCO with multiple multiplier stages, because a human would have to tune each of those stages.